The average kinetic energy E in joules of nuclei is related to the absolute Kelvin temperature by. There we go. So they just give us this formula, right? Notice there's no units, but that's okay. Determine the temperature for which the average kinetic energy of the nuclei is 9 points. Well, are you going to plug that in for here? Are you going to solve for T? There you go, right? And the nuclear fusion of deuterium and tritium occurs at temperatures that are less than that temperature, right? Well, remember that when we're figuring this out, this is the average kinetic energy. But remember this, the simulation when we had all those little particles bipping around, right? Remember that some are going slow and some are fast, right? The overall distribution, this is the number of particles, this is the velocity, is like this Maxwellian distribution, and there's plenty of particles that are going well faster than the average, right? So talk about that. It's possible for, I mean, if the average is below that ability to fuse, there certainly are some particles that are going faster than that, right? And then the other possibility, and I wrote this down, I think this actually is a thing, is that the Heisenberg uncertainty principle, I hate to bring this up, but because they didn't put it on the mark scheme, presumably I would have missed that mark if I'd written only that. But I do believe that the Heisenberg uncertainty principle has something to do with it as well, that a lot more fusion happens than is justified by classical physics. But anyway, it's not in the mark scheme though, so maybe it's wrong, but I don't think so. And then explain the need for high temperature for nuclear fusion to occur. What do they say? You need to, it's like 2 marks, right? So they have to overcome the Coulombic force, right? The repulsion between 2 charged particles, right? And if the high temperatures mean that they're moving faster, so therefore the kinetic energy can help them overcome that repulsion, right? Let's put this, let's just say that in English, right? The hotter it is, the faster these 2 particles might be moving toward each other if they're on a collision course. And they have to go fast to overcome the repulsion because they're both positively charged, right? And then let's see, so suggest why for large separations of the nuclei, the force between the nuclei is repulsive. Well, for large separations, it's the electrostatic force that's predominant, or the Coulombic force. But when they get close enough, because the strong nuclear force is short range, okay, because it's short range, if they get close enough, it's much, much stronger than the Coulombic force. Obviously, it's what ultimately holds the nucleus together. So those are the words you need to use.